Hi, we've talked about the humble resistor on here a fair bit over the time, and I've done the recent blogs on the decade resistance boxes and how you can build your own, and we've talked about tolerance a fair bit, but what exactly is the tolerance and how does it vary in your typical metal film resistor like this? And it's a good question, and it's something you can't really find in the data sheet, because you read the data sheet for one of these things and it says, you know, it's plus minus 1% metal film resistor. Well, okay, where is that actual value of this resistor going to fall within that 1%? Is it completely random? Is it shifted towards one end? Do they manufacture 10% tolerance resistors and measure them and then mark these ones and sell these ones as 1% and sell the other ones as 5%, sell the other ones as 10%, etc.? How do they do it? They don't really tell you on the data sheets, and getting info on that sort of thing is hard. So just what is the probability distribution, that's the technical term, of the values of a typical resistor like this? You damn well can't really find it in the data sheets. And well, is it that I've always assumed, I've never actually measured it, I've always assumed, and you know, from industry knowledge, it's just assumed to be a typical bell-shaped or what's called a normal distribution or Gaussian distribution response. But is it? I don't know. I've never actually seen the manufacturing graph for a resistor, or not that I can recall. Maybe I have, but I don't know. If you can find one somewhere from a manufacturer, point it out. But I thought, well, bugger that. It'd be interesting to actually measure it. What are these resistors and what is their probability distribution? Well, it's easy to find out. You get a whole bunch of resistors and you measure them. Let's go. As you saw in the decade resistance box video, if you take a bunch of 1% resistors and you put them in series, then your total, that's how a decade resistance box works, put them in series and you'll end up with the same tolerance as the single resistor. So if you've got a 1% tolerance resistor, you put 10 in series, it's 10%. But if you put them in parallel combinations, you can actually end up with a better, like if you want 1K and better than 1%, but you've only got 1% resistors, if you put 10K resistors in parallel, you should end up with a better tolerance resistor than that 1%, if it is actually a true bell-shaped Gaussian normal distribution around that center mean value. If it's not around the center mean value, if that center mean value is shifted to one side or the other, as it could be, then you're not going to end up with that 1K. You're going to end up with something shifted down the side. And it all gets quite complex. If you want to actually do the math behind it, that can actually get quite complex too. So anyway, I thought we'd measure them and see what we get. Now, there's actually two sides to this issue. One is the case where you've got all of these resistors and they're manufactured from the same batch because they're on this same bandolier. You can pretty much be assured that these were manufactured at the same time, on the same bit of equipment, on the same day, by the same operator, with the same materials, etc., 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 at the same temperature, yada, yada, yada. So there are quite a lot of process variations. So, but because these are all from the same batch, that's one issue in itself. That's one thing we want to find out. We want to know what is the probability distribution of the resistors in a same production batch. And then the second issue is if you take 10 resistors and put them in parallel, but if you get one resistor from separate batches that are all a year apart, well, is that distribution going to be the same as what you get from a one manufacturing batch distribution? It sounds complicated, but they are two separate issues. But because I don't have, known separate resistors from separate batches, and all that sort of stuff, we'll just look at this case today. But this should reveal, hopefully, something interesting, because when you measure and plot data, you'd be surprised at what can come out of the end of it. I don't know what we're going to find. Could be boring as batshit. And as always with electronics, you find some real interesting stuff when you start measuring things, collecting data, and just the simple aspect of graphing it. In this case, we're going to get a probability distribution. And we may or may not find something really interesting, but we don't know unless we actually try it, take those measurements, go to the effort to do it, see what pops out the other end. I have no idea, but it's going to be fun. Let's find out. Now, the resistors we're going to use today are some I've had in my possession for quite some time. They're a Philips brand. I don't know the exact part number. Might be able, it's torn off, as you can see there, but I believe they are 1% metal film resistors. Now, this will probably only be valid for this particular type, metal film, because there are many different types of resistors. There's, you know, carbon composition resistors, and there's thick film resistors, thin film, and there's wire wound and all sorts of things. So, you know, we're only going to do metal film today. Now, just because we don't know the exact part number for this resistor doesn't mean we can't figure out what it is based on the color-coded bands. Now, it just so happens this is one of these 6-banded resistors. Now, in this case, it's got brown, black, black, brown, brown, red. And this red one, this 6th band on the end here, indicates the temperature coefficient, and that can vary. If this last band here, if the sixth band was actually brown, it would mean 100 ppm, but because it's red, it's actually 50 ppm, and if it was orange, it'd be 15 ppm, and yellow would be 25 ppm. So you can actually work out the temperature coefficient of that resistor. Now, of course, if this was a regular 3-band resistor, you know, a 5% tolerance one or whatever, if it only had 3 bands, then it would, of course, for 1K, it would be brown, black, red. And if it was a 4-band resistor, it would actually have brown, black, black, brown. Now, the 5th band actually indicates the tolerance. In this case, it is brown, and that indicates plus minus 1%. If it was red, it'd be plus minus 2%. If it was green, plus minus 0.5%. Blue, 0.25. Violet or purple would be 0.1%. And if it was grey, it can go down to 0.05%. Now, I know that this is probably enough because 1K plus minus 1% is 10 ohms. So it's going to be plus minus this second digit here. But, you know, I just want extra resolution, and this is where resolution counts. And also, with this sort of test, you're going to want stability. And once again, the Fluke 87 is more than stable enough for a measurement like this. But hey, I've got a HP 3470A bench meter with an extra digit of resolution and better stability. So hey, why not? Let's use it. So let's gild the lily, shall we? And use the 5-digit mode. I mean, you know, the 3478A has got a 4-digit mode to mimic the Fluke 87, or even a 3-digit mode if you're that way inclined. But we'll use the 5-digit mode. It's warmed up, so it's nice and stable. And the other thing which can affect this sort of measurement is the change in temperature over time. So we'll just monitor that as well. But I wouldn't expect a major change. These are fairly low ppm value resistors. They're probably 50 ppm or something like that. But I'll just monitor the temperature change over the span of, like, I don't know, what, an hour it's going to take me to actually measure these things or something. The temperature shouldn't change that much. So, but if you're doing, you know, this sort of stuff seriously, then you have to take those sort of things into consideration. Any changes in temperature, just physically handling a single resistor like that can actually heat it up and change its temperature, even touching the leads. You're actually heating up that resistor. So, you know, you've got to, handling can be important, those sort of things. And of course, the other thing you have to consider is the repeatability of your probing system. Now, in this case, we've just got these regular 4mm banana plug to alligator clip leads, you know, fairly cheap ones, but they should do a fairly decent job of actually biting through any oxidization on the leads, and because we've got 1K, it's not going to be a huge differential. If we were measuring like a 100 ohm resistor or something, it might matter, or a 10 ohm resistor would be worse. Then the contact resistance could vary a bit, but on 1K, it's pretty good. And if we short them out, let's have a look. There we go. It's 160 milliohms, 150 milliohms. Take it apart. Put it back together. There you go. It's going to be within plus minus, one least significant digit there. And if we just disconnect there, wiggle these around, all that sort of thing, just make sure you test the repeatability of your system. I'm fairly happy with that. Now let's actually put it, when you short the things out, but let's actually put it on a resistor leg, shall we? And no, yeah, there we go, it's the same. So we're obviously, we're biting through any contact resistance there, wiggle those around, and that looks pretty repeatable to me. And, down to the order of, 100 milliohms. And there's our first resistor in this batch here, and really, I've left it for a while, and it really hasn't varied much at all, plus minus at most 2 least significant digits. So, I'm fairly happy with that, and I've played around with the probing, and I've swapped it around, and I've also got it on fixed manual range here, so it won't auto range or anything like that. And I'm fairly happy that this will give us consistent results. So I'm going to go through, measure each one of these resistors one by one. Maybe I won't do the whole lot. I'll do it until I get bored, and enter the values into an Excel spreadsheet so we can do some analysis. Woohoo! Data analysis. Great fun. And just to make sure that there's no funny business with this bandolier and the glue, well, there's a little bit of glue that's actually used inside there, and there could be some contamination, some impedance across there between resistors, so there might be a little bit in parallel. Who knows? Well, let's check that here. 999.51 ohms. Let's take it off. Pull it out, and 999.52 ohms. There you go. Not a problem. I'm happy with that. And it actually took until resistor 129 until I found one that shows spot on 1.00000 k ohms on my meter. What does that mean? It means absolutely nothing, because it's not even true, because I haven't zeroed the thing out yet. But anyway, just thought I'd share that with you. Resistor 129. Winner. Whew. Well, there you have it. I did actually get through all the resistors, and I stopped at 400. They were like 402, but there you go. 400, nice round number. Lots of data to work with. I really like it. The temperature only changed 0.1 degree over that time. Not that it really matters, but we've got a lot of data to work with. Now it's time to graph it, play around with it, and see what pops out, because often you can get some mysterious results pop out, but only if you try it. Okay, here we go. We've got our data, and let's do some analysis, shall we? Now, column A here is all the 400 measured values which I entered directly from the meter, but the meter didn't zero out the lead resistance. So I've done that here in column B here. As you can see, I've actually subtracted 0.15 there, which was the constant lead resistance and contact resistance we had. I subtracted those, and so column B is the true measured value of the resistor. Now, column C here, I've calculated the variation from a nominal, in percentage, from a nominal 1K value. So that gives us our plus minus deviation, which we're interested in, because the resistor obviously has a claim spec of plus minus 1%. So it's easier for us and clearer if we work in a percentage based value. So that's exactly what I've got. So column C here is the data we're actually going to plot and work from. Now, if you go down here and you plot column C there on a regular XY graph here, you'll see on the x-axis here are all of our 400 values, and you'll notice that they're scattered pretty much as you'd expect. No surprises in the actual scattering, and the mean is pretty close to spot on 0 there. If you just do it by eye, close one eye and squint a bit, and you can see that the nominal is going to be, reasonably close to 0, so no surprise there at all. But one of the big surprises I found is that no value went over plus 0.6 or minus 0.6. Actually, it's about plus 0.5. No value went over that. So that was a surprising result. I expected to get values very close to the nominal, claimed spec of plus minus 1%. But it turns out these resistors seem to be much tighter tolerance. I mean, out of 400 resistors, I expected at least a few outlier ones to be right out near that, 0.9, 0.8% at least variation, but we didn't see that. It's the biggest values are plus 0.5% and minus 6. Very surprising. And if you're curious to know what the actual nominal average value is, it's 999.72 ohms. There you go. And I guess the other thing to note is that the resistors 1 through 400 here are actually in sequence as I measured them on the bandolier, from one end of the bandolier to the other end. So there are no sort of oscillations or anything like that in there that are immediately apparent. So they are actually truly randomly scattered. So I think if you mixed up those resistors and measured them all again, or just unsorted them, did a different sort on that and just randomized it, you'd get the same result. So that brings up another interesting point. What do we get if we actually sort all of the values from lowest to highest, or highest to lowest? It doesn't really matter. So we're going to select these columns over here. We sort ascending, and as you can see, the values in column C there are now sorted. What does that give us on the graph? Bingo, there it is. And no surprises for me at all. This is exactly, I've seen this countless times, this is exactly what I expect from a bunch of random data and a Gaussian distribution at that, which we'll get onto. Sorted graph of just random data, because if it's a bell-shaped Gaussian distribution, you'd expect to sort of get most of your values like this. So the slope in the middle here to be quite shallow, and the slope just gets steeper and steeper at the ends where the outliers are, because there's fewer outlying values. So that's a very typical Gaussian type response for random data, and this particular method is useful for showing offsets better and things like that. Ideally, you would, if you had 0, you'd expect it to be right smack in the center of the graph there, but you can see there is a little tiny offset in there, and this is just another useful way to interpret the data, but no surprises there at all. So I think we're going to get our Gaussian bell-shaped response when we do our frequency analysis. Now, what we want to do is some frequency analysis. Now, it's similar to the difference between time domain and frequency domain that you're probably used to. In this case, this data over here, it can be considered the time domain data, and the data we're now going to analyze to get our histogram is the frequency domain data. And the way this works is you create different bins. In this case, I've got 21 bins ranging from 1% down in 0.1% increments down to minus 1%. And we want to find out how many of these particular values appear in each one of those bins. So we're doing a frequency sort here. So we're going to use the frequency command, which is available in Excel or OpenOffice, which is what we're using here. And it takes all of this input data in column C here, and it analyzes all this data and counts how many of a particular how many items actually fall within each one of these bins over here. And the way you do this is you use the frequency command. It accepts 2 input parameters here, and as you can see in the help pop-up here, it's got data. So the first part of this is the data set, in this case C. We want column C here, and we want all of the data. Now, a little trap here is you've got to put in the dollar signs there and there, and there. Now, the reason you have to do that is because when you actually create this thing and then drag it down like this, you want all of it will actually increment that C value unless you put the dollars in there. And for each one of these, you want to sort through all of the data. So putting the dollars in there ensures that you actually do that. Now the second one up here is actually called classes, but it's bins and is the other name for it, which we're going to use here. So these bins are in column I2 to I22 down here, as you can see, and we've got those 21 bins, and the frequency command is just magic. It just goes through and counts the data in those bins and converts it effectively into the frequency domain. So then, once we've got the data here in column H in the frequency domain, we can just plot it exactly the same as we did before, exactly the same plot, except we're doing a column graph, and bingo, this is the response we get out of this, and that is our histogram. And as you can see, it does show that normal distribution exactly as we were expecting. No surprises there at all. It's centered it's centered on 0 there, around about 0, and but the big surprise, of course, is that it only extends to plus minus 0.5%. There are no outlying values right out here, as we saw in our other graph, but it's clearer here that the because this effectively represents this distribution, normal or Gaussian bell-shaped distribution, effectively represents the probability of one of these resistors actually being manufactured out here in the outliers. As you can see, most of them are going to be within the tight 0% bin there. A good lot of them are going to be plus minus 0.1% either side of that, and a fair number plus minus 0.2%, and then you start getting into the outliers out here, and once you get to 0.5%, well, there's just almost nothing left. There's only a couple of items down in 5 or under in these sort of bins. Now, it's not a perfectly shaped bell-shaped curve there, or Gaussian response. You've got to use your imagination a bit. Like this one here in the 0.3%, it should have been up a bit, and this one should have, these should have been down, this one should have been up a bit here and up a bit, and well, in an ideal world, that would be an ideal shape curve. And really, with a true random set of data, as you'll get with a manufacturing process like this, you will ultimately get that, provided two things. Provided A, that you have enough data. Now, in this case, we've only got 400. Now, 400 sounds like a lot when you're, and it is a lot, when you're plotting just the data like this. That's an awful lot of, data, more data than you can poke a stick at. But when you're doing frequency analysis like this, you're left with fewer and fewer actual items in each bin when you actually convert it into the frequency domain like that. Now, we can change this by increasing the number of bins we've got, and that's what I'll do over here. But then you effectively halve your number of data in that particular bin. So when you're doing frequency analysis like this, the more data you have, the better. It's very important. And in theory, if we had an infinite amount of data to work with, and we did a large enough number of bins, then we would find ultimately that it would average out, and we would get our perfect normal distribution Gaussian response curve. So as you can see, this one's a bit rough and ready here. It's it really is a rough as guts kind of thing, but you can still see, because we are expecting that Gaussian response, you can actually see it, and it is there. But what happens if we increase our number of bins? Now, I've done exactly the same thing here, except I've got 41 bins instead of 21. I've actually doubled the number of bins here, and as I said, you halve the number of items when you do that. So you can't just increase the number of bins to an infinite amount, because then you'll end up with no data at all in each bin, or one item in randomly spaced bins, and it'll be useless. So, but the more data you have, it's beneficial to have a higher number of bins like this. And our highest number here is 61 here. That's not too bad, but when you start getting to the outliers down here, you know, this one's 0 and this one's 1, and, you know, it's a bit over the shop there. But anyway, I've done exactly the same thing, exactly the same formulas here, except I've got twice as many bins. And when you plot that and you go over here, here it is. There is your response. And as you can see, it's a bit more fine detail because we've doubled our number of bins. And as you can see, there's probably a slight offset there on the negative side of things, as you'd expect because we've got a slight negative offset. If you look down here, you remember we had a slight negative offset in our average value, and also you saw that on our sorted graph, and that manifests itself on the histogram here by having a slight offset. And if you're not centered around the mean, this histogram will actually move either side like this. But I'm very impressed and not really surprised that the manufacturing tolerance for these good quality Philips resistors are actually right on that 0%. Now, the really interesting thing though is that, as we've said before, it sort of peters out at 0.5 plus minus 0.5%, not the plus minus 1%, which we were expecting. So this kind of, well, it doesn't really bust the myth, but it does in this case, for this particular batch from Philips, the metal film resistors, at this particular time manufactured in this factory, they clearly weren't targeting, as a lot of people claim, that they manufacture, say, 5% resistors, and then they test them all, and the ones that pass to plus minus 1%, they sell them as, mark them and sell them as plus minus 1%, and the others they sell as plus minus 5%. Well, that's clearly not the case, because if that was the case, you would expect, well, I would expect a response which is much shallower. It'd still kind of be like the peak, the top sort of peak of that Gaussian response. So I would have, because imagine if this is plus minus 5% here, okay, and then we're getting the plus minus 1% bin, so we'd only be seeing that little bit over there like that. So that would manifest itself maybe in a graph which started out, say, at 30 here, and let's say 20, down at 20 here, and sort of went up and peaked like that pretty quick, and then rolled off sort of, you know, once again down at, say, around about 20 here for argument's sake. So it would have been much flatter, and we would have seen a reasonably large number of resistors out here at the 1% limits. And that, if you get the cheap one hung low resistors or something like that, you buy them from, you know, off eBay, and you measure them, then they could very well be 5% resistors tested as 1%. Who knows? I don't know. Maybe they don't do that anymore. Maybe it's a myth these days. Maybe they did it in the old days, but these days they would have targeted. They could target their manufacturing processes. As you tweak them, they can get better and better. And that's what Philips have clearly done here with these resistors. Their manufacturing processes and tolerances are obviously geared around a plus minus 0.5% manufacturing tolerance. So maybe they sell these resistors, they target and market them as 0.5% resistors, and they sell those as plus minus 1% because they know they're going to be well within plus minus 1%. And maybe when they sell them and mark them as 0.5% resistors, possibly they lose a few, percent. They might be losing 5% of their resistors out here and out here, but there you go. They're clearly targeting 0.5% resistors. So ultimately, what these kind of manufacturing normal Gaussian response curves show, it's typical not only for resistors, but most other components as well. You're going to get this sort of manufacturing response. If you've got a noise floor of an op amp or something, it's going to have this same type of Gaussian response. And what it basically represents is a probability, or the probability of a particular device you buy. In this case, it's a resistor, but it could be an IC or an LED with its brightness or whatever, where it's going to fall within the probability of you getting a device which falls within this range. And as you can see, the highest probability is going to be smack on 0 like this, and the next highest, and you've got a fairly good chance that you're going to fall within that plus minus 0.1% range, at least for these Phillips resistors. Remember, this may not be the case for some cheap one-hung low brand resistors or something like that. So, but your odds of getting a resistor that's, right out here, in this case, for this particular batch, the odds of getting like a 0.8% resistor out here are almost bordering on 0. I'm not going to say it's not possible, but it's very, very unlikely. And getting one right at the 1% limit, in this particular case, well, it's pretty rare. I mean, we had 400 resistors. I guess that's not a huge number, but if you got 40,000 resistors or something, you might see a few that sort of poke their head out, just like this one did at 0.55 out here. Ultimately given enough time, anything is given enough numbers, any probability. There's no such thing as a 0 probability out here. They can actually appear, but it's very unlikely. And the other thing to remember with these responses is that they can shift like this, and this will be in the manufacturing environment. They will actually do plots like this, either daily or weekly, to track their manufacturing and how it's drifting. And you might see the peak actually drift back and forth as you change, various, change materials. You've got suppliers. You change workers who are operating the machinery, perhaps. If it requires some sort of manual process or manual intervention or something like that, and you can watch your processes drift, or if your temperature's changing in your manufacturing environment, that can alter things and all sorts of things. So you can get really some good insights into manufacturing, whether components or products or whatever it is you're manufacturing, using this frequency analysis. It's a really good tool. So I hope you found that interesting. There are a couple of surprises in there, but there you go. We got our Gaussian response exactly as we expected. And if you've got more data on how they actually manufacture these things these days anyway, then yeah, send us the information. I'll catch you next time. Probability distribute. So just what is the probability distribute? Probability distribution. Planes flying over. Got to stop filming. Go figure. Geez, you think I'm in the flight path or something instead of out here in the suburbs.